Hi, everybody. I actually got a request, but somebody wanted to know a little bit more about the periodic table, kind of how atoms work, their personalities to a certain extent. So I thought I'd do a little bit more in depth. We'll be covering a lot of these topics throughout the course as we go, but I'm going to go a little bit more in depth than what I did before. And so one way when you look at a periodic table is to realize that there's a lot of stories within it. There's so many groups and all the personalities of how each element reacts and how they interact with other elements, is incredibly complicated. So obviously I can't cover everything, but I'm just going to kind of give you some just sort of overviews of like how they function. And I'll start with different groups and start with the noble gases. So we have this group over here. And so people will learn noble gases. Why do they call it noble? Sometimes people learn this. They say, well, the noble gases are like a king. The word noble, not Nobel Prize, that's a different name. Like the king, he doesn't interact with the commoners very much. And so these gases were discovered as people learned to liquefy air. So you would liquefy oxygen and nitrogen, and they would find these gases in there that couldn't react with anything. And they started realizing that there's like little bits of argon, for instance, in the air that we breathe. A little bit less neon, almost no helium, because helium is so light that it actually is fast enough that it can escape the Earth's atmosphere. If you wonder where you get your helium balloons from, there's mines that trap helium that comes out from cracks in the earth from deposits of uranium, that as they decay, the uranium releases alpha particles. Those turn into helium, and they're slowly ooze out of the earth. So, kind of a strange concept. You'll often hear that they don't react with anything. That's not entirely true, and as we'll see later in the class, xenon and krypton especially have compounds that are made by a guy named Neil Bartlett at Berkeley. He was at Berkeley. I'm not sure where he discovered these originally. Anyway, so there's sorts of xenon compounds, I think I got that right, that have been made. So there actually are some compounds of xenon. There's a few of krypton. I believe there's one argon compound that's not stable and can only be produced at low temperatures. But so there are some. So there's a little bit more chemistry going on than you maybe have previously heard. When we move on to this group here, the halides, they're quite fascinating, and fluorine is sort of the king of reactivity. It's the most reactive molecule. So F2 is a strange beast. It's not that easy to make. If we go down the list, chlorine, bromine, iodine, all of these fellows pair up with each other. This fellow, astatine, radioactive. It's not like a real compound. You don't see it in any kind of macroscopic form. You might know like iodine from getting a cut, and there'll be like an antiseptic that has iodine water. You can buy in grocery stores still. Yeah, people use it to like put on a wound to kind of cleanse it. So iodine is the least reactive. Bromine a little bit more so, although it's pretty rare and you don't see it. Chlorine is used to clean pools, disinfect swimming pools. You can produce it with that jug of chlorine. It reacts with the acid and makes chlorine gas, molecular chlorine. But fluorine, very rare. You never see it outside of chemistry labs because it's extremely reactive. It's got a lot of crazy properties. And just as a side note, what I would recommend doing is, when you get some time, because you have so much, check out the periodic table of videos. It's a series by a British fellow with, he's everything you want in a chemistry professor. Old, great hair, funny, British. And he has videos where he goes to different labs and like looks at elements. Like, so most chemists have never seen fluorine. It's extremely hard to work with. It has to be used in stainless steel containers, all sorts of crazy stuff. So he has some videos demonstrating like what it actually looks like, and it's just rarely rare because until these videos came out, there's many of these elements I've never actually seen in person. So if you notice as you go further down the periodic table, you get a little less reactive. That's actually sort of a common, well, that's not always a common trend, but in this group it is. If we follow along the second group, they have a name, but we'll skip it. The group 6 elements, the oxides, you have oxygen, sulfur, selenium, tellurium, and lastly, polonium. Polonium is another one of those at the bottom, radioactive, you're never going to see it. It's unstable. Oxygen, obviously super common. Right? Sulfur, very common. You can dig it up out of the ground. It's that sulfury smell. Selenium and tellurium, much more rare. Generally speaking, as you go down the periodic table, they become more rare, less common. And that's because elements are formed in stars and supernova and sort of big events that are galactic in scale. And so it's easiest to form elements that are smaller. The bigger elements are only formed when things like supernova explode or neutron stars collide with each other. There's a lot of strange physics there. So the big heavy ones are much more less common. This kind of group here, whoops, you know, is sort of the most interesting group. Boron, carbon, silicon, phosphorus, nitrogen. They all have the most complex chemistry because they form the most covalent bonds, especially carbon. And to me, those are the most interesting ones. Carbon is just, there's an entire course called organic chemistry, an entire field dedicated just to carbon's chemistry. Okay, so let's move on a little bit and talk about a few other things. This group, you know, here, they're called the transition metals, you know. And at one level, if you were to look at a periodic table sample, they're all going to look the same. They're all just a bunch of metals, maybe with the exception of mercury and gold. But at first glance, you know, you can't really tell a polished piece of iron from a polished piece of chromium or nickel, you know, maybe at first glance. Platinum kind of looks the same as silver. It's not super dramatic. So they kind of all have a similar quality, but the more you look into it, the more distinctions there start to be. And you can kind of tell right off the bat by these numbers up here, the 3, 4, 5, you know, 8, 1, 2, the B groups. And that tells you a lot about the charges. So for instance, zinc really always forms a +2 charge. Cadmium always forms a +2 charge. But mercury down here always forms a +1 or +2. So he has more variety. Similarly, well, sort of like that, copper can form 1 or 2. Silver, 1. Gold, usually 3, but also 1 apparently. So these kind of relationships are very complicated. You have to spend quite a bit of time memorizing and really getting to know each element and knowing what are the oxidation numbers, what are the states that each one will find itself in. It's not very obvious. There are rules to it and there's explanations why, but they tend to be fairly complicated. So at the beginning, most people don't learn. When you get down to these, moving all to way to the left on the periodic table, is the alkali metals. And they do have a really interesting history in terms of they were among the first metals to be produced. Like, you know, you can't dig any of these things up. They react immediately with water and they react quickly with air. If you just leave a chunk of sodium or potassium sitting around, it just quickly deteriorates and turns back into sodium hydroxide. So the, you know, around the late 19th century, people started figuring out how to reduce, I believe they used carbon, I should look that up, to produce sodium and then water and like carbon monoxide. And so you would put these things into, you would put lye, which is a base, and then put it into rifle barrels, like literally like metal tubes, and sealed one end and then heat it up with like a blowtorch until they drove off other stuff, and then out of it would come this metal that they would distill into like an oil container. It looks something like this, like you had a sealed container and they had like a little container of oil. and you heat the sodium hydroxide up, it vaporizes and like ends up in the oil and comes out as like little droplets. So there's reproductions of this experiment on YouTube where people have done it and kind of reproduced the old experiments, and it's kind of interesting to watch and see how people actually did it. One thing to note is that as you drop down this way, kind of unlike the halides, they get much more reactive. So the lithium in it's reactive. If you put it in water, it sparks a little bit, or it'll quickly react. Sodium, much more so. You see it jumping around. Potassium, pretty much as soon as it hits water, will light up and start flying around. Rubidium, really expensive, but you can watch a YouTube video on it. There's a Mythbusters where they throw some in. Really violent with water. And cesium, I think a video once, it's like, it just pretty much goes boop. The second you get it, it's really expensive. Francium can't be produced in any kind of real amounts that you could see. So anyway, those trends typically are the same with these guys, the alkali earths. They have a very similar history. The alkali metals being +1, alkali earths being +2 always. Magnesium, calcium, strontium, barium, radium. So as you drop down, they get more reactive and a little bit bigger. Beryllium, by the way, fascinating metal. Beryllium is one of the best metals to make stuff out of, potentially. It's light, super strong, like lighter than aluminum, extremely strong, somewhat pretty flexible from what I understand. And early on, when they first discovered it, they thought this is going to be the miracle metal. It's kind of rare, but they thought, they were trying to make bicycle frames or missile components out of it. It turns out that it's super toxic. The dust is really poisonous. And so all the workers who in the factories who would work with it would eventually develop terrible lung diseases, lethal lung diseases. And so it's really rarely used. It's pretty much only used for aerospace military applications. And I think the James Webb Space Telescope is made out of beryllium, but they had to do a tremendous amount of work to keep, with like air filtration systems, to keep people safe using it. So kind of interesting history. Okay, last little bits are these two groups here, the lanthanides and the actinides. These are called rare earths up top. And they're actually not really very rare. One of the reasons that they're expensive, though, is that they all have a +3 charge. Almost all, I should say. They love to be +3 charged. It's just kind of their personality. And because they're all basically the same size, they all have the same charge, they're very, very difficult to separate from each other. The technology needed to, when you get an ore, and they often occur mixed up together, to kind of clean up one and get a pure sample of one versus the other, could be technologically complicated. So getting the ore isn't the problem, although there's not a ton of this stuff around, but there's enough of it around that it's not that rare. So we can dig it up, but processing is actually the real big problem. That's the expensive part. Last bits are the radioactive ones, and uranium is fairly common. People don't realize this. It's about as common as tin in the Earth's core. It's the last one that really occurs naturally. Neptunium is pretty rare. There may or may not be some plutonium floating around, but probably not. All of these ones here, the transuranic elements, transplutonic they're called, are going to be man-made. They're usually made in cyclotrons, where you spin an element around in a circle and collide it with something else. And then when the two of them collide, they form a heavier element. So they're made by bombardment. Sometimes in nuclear reactions they occur, but usually they're made by bombardment. So a lot of times when you see these little brackets, that's an indication that it's highly radioactive, that there's no stable forms. And usually that means you can never see it with the naked eye. No one's going to produce a piece big enough to see, because if you did, it would be so radioactive it would just melt itself from its own heat. Okay. A lot of the reasons why this is happening relate to this kind of weird notation, which we'll see later in the class, and I'm not going to talk about it too much. But you'll see examples, carbon, and then these sort of 1s2, 2s2, 2p2 notations. And what this means is this tells you about how the electrons are arranged. So the secret to all the chemistry and sort of what we know about these things is how the electrons are all arranged. So we're going to cover that a lot in later chapters. Anyway, I hope that was a little bit more background if you're interested in it, and best of luck.